Okay, now we consider the geometric interpretation of the Hahn-Banach theorem. We first give a definition for maximum linear subspace. So suppose we have a linear space. Okay, and also M is a proper linear subspace. Then we say M is maximum if suppose M is contained in Y and is contained in Z, implies that Y is equal to X. Okay, so that means if you ever want to increase M to another linear subspace, extend to another linear subspace, and this linear subspace has to be the entire X. Okay, so that's the definition for maximal linear subspace. Okay, so this seems to be a very intuitive definition, but it's difficult to operate in practice. How do we characterize such a maximal linear subspace? The following proposition gives a very clear equivalent definition for the maximal linear subspace, which says as follows. Say I have, again, a linear space, and the M is a proper linear subspace. Then M is maximal if and only if for any X naught not in M, we can write this X as a direct product, a direct sum of this space, which is just a span of the X naught, where A is in R, just as write it as a direct sum of this and M. Okay, so it's a maximal if and only if we can rewrite. You can write this X as the direct sum of these two spaces, where this is just simply a span of the X naught. Okay, so let's see how do we prove this. Let's first show this direction. So we consider this X naught to be the direct sum. So for any given point X naught, we define this space X naught to be the direct sum of this. And then we just need to show that X naught is X itself. Okay? And if not, then there exists another point. We call it, say, X1, which is in X, but it's not in X naught. Then, apparently, when we take the span of X1, and the X naught, we can see that this is again a linear subspace, and it is contained in X. Okay, but on the other hand, it contains X naught, which is not the same as X as this direct sum, since X1 is not in X naught. Okay, and also the M is not in X naught either, because there is a point X naught that is in X, that is in X naught, but it's not in M, right? Because this point that we chose, this point that we chose, it is in X naught, but it's not in M. Okay, so we have that. And this is a contradiction to the fact that the M is maximum, because by definition, if there's any other linear subspace that contains M as a proper subspace, then this linear subspace has to be the original X. But now we show that X0 contains this M as a proper subspace, but X0 itself is not equal to this X, because it's contained in this space, strictly contained in this space right here. Okay, so that's a contradiction, which contradicts to M being maximal. Okay, so that's this direction. The other direction, so let's say that if we want to show this maximum, let's say that M1 be a linear subspace such that M is contained in M1. Okay. Then we just need to show that M1 must be the original space X. And to show this, we just let the X now to be from the M1 minus M. Okay, then we know that the A X naught, this span of X naught, direct sum of this and M must be equal to the X as we said on the right hand side. That's what we know. Okay, X naught right now is not the M. Then the direct sum must be equal to X. But on the other hand, we know that this is included in M1 because M1 is a linear subspace. So it contains M, it also contains X naught, so it contains the direct sum of these two. Okay, but on the other hand, this M1 must be included in X as well. So what we have is X includes the M1 and includes X. So this implies that the X is equal to M1. And this completes the proof, since we showed that for any linear subspace M1 that contains M, we must have M1 equals to X. Okay, so this completes the proof. Okay, now I'll give another definition called a hyperplane. Okay. So the hyperplane is nothing but just a simple translation of a maximal linear subspace. Okay, so we say that L X naught plus M is called a hyperplane of X, where this X naught is some point in X, and this M is a maximal linear subspace of X. Okay. So you just think that in a 3D case, a maximal hyperplane is something like that. It's a two-dimensional space, two-dimensional plane passing through the origin. And the hyperplane means, so this is a maximal linear subspace, this one here. Okay? And the hyperplane is just a translation of this to some point. Say we translate this to a new point right here. And there's a point that is X naught. This is a hyperplane. Okay, just like what we interpret in the Euclidean space. But right now we're in a general linear space, which could be infinite dimensional. Okay, that's just the extension of the hyperplane in the Euclidean space. Okay, then the question we're interested in here is how do we characterize the hyperplane using linear functionals? So this is given by the following theorem. So what it says is, let's say we have linear space, but not just a linear. It is also equipped with a norm. Let X be a B star space. Okay, then L is a hyperplane in this space X if and only if there exists a non-zero linear functional. So from X to R, and f is not zero. It's non-zero linear functional. That means it must be non-zero at some point. Okay, such that or I should say not just this linear functional, but also some real number. Let me write it this way. If and only if there exists some f non-zero linear functional f from X to R and some real number R such that L equals to L of R. So what this means is this is by definition all the points in X such that f of X equals to R. Okay, that's the meaning of this L of R. Okay. So we're trying to show that a hyperplane in X is nothing but HFR for some f, for some linear functional f and real number R. Okay, so let's prove this. Let's first define the null space. The null space of f is essentially just a HF0, right? Because by definition, as we saw earlier, this is just nothing but just a null space of f. It's just all the x such that f of x equals to 0. Okay, so that's our notation. And this is the linear subspace of x. Right, this is the linear subspace of x. It's really easy to show it's linear subspace of x. And now for any x1 in the x, but not in HF0, and also for any x in the space x, we can see that the x must be, we have, say, we have that the x minus f of x over f of x1. Remember that x1 is in here. So that means f of x1 must be non-zero, right? That's how we can put it on the denominator. Now let's look at this. Look at this point. This is a linear combination of the 2 points, so it's still in the space x. But we're going to show that this is not just in space x, but it's actually in the HF0. The reason is when I apply f to this, I'll get f of x, because f is linear, minus, as you can see, f of x over f of x1. This is a constant, so I pull it out, and I have this. But you cancel that, so you won't have fx minus fx, which is 0. Okay, and this means this point right here is in HF0. Okay, or in other words, this x is in this space, or in this set on the right hand side. Just a translation of the HF0 by that. Sorry, x1 here. Okay. Okay. So right now we said that this is a HF0, and as you can see, any x can be written. This means that any x can be written as some constant times x1 plus some element in this, right? So this means that the x can be written as the direct sum of ax1 for some real number a plus direct sum of this, because any x, as we showed, any x can be written in this way. So that's why the x is nothing but this direct sum. Okay, and according to the previous proposition, right here, we say that if we can show that x is equal to this for some linear subspace, then this linear subspace must be maximal. And that means HF naught is maximal. Hence, HF naught is maximal by the previous proposition. Okay. So we showed that this HF naught is a maximum. And I'm going to show that the HFR, for some R, the HFR is this L. And by definition, this L is a hyperplane. Okay, because we said that the hyperplane is just a shifting of the x naught to shifting of some maximal linear subspace by x naught. So let's see how do we get this. Okay, so to do this, let's first look at some x naught. So now let's say for any x naught, which is in x but not in HF naught, then we set R to be f of x naught. Okay, we know that x naught must be non-zero because it's not inside HF naught. And also, we define this HFR to be the set of points whose function value is equal to R. Okay, so let's see what happens from here. Right, because of this, we can see that if x is in HFR, then this means that f of x should be equal to R, right? And this means that f of x minus x naught, according to, because f is linear, so I know this is just f of x minus f of x naught. Okay, and because f of x is equal to 0, so this is equivalent to this R minus R, which is equal to 0. And this means that the x minus x naught should be in HF0, right? Since f of x minus x naught is equal to 0. And this means that x is in x naught plus HF naught. Okay? So that means a point that is in here if and only if the point is in this. Okay? So this is the L, your definition. And we said the point is in L if and only if it is in this. And this means that the L is a hyperplane, because we said a form of this, or set like this form, where this HF naught is a maximal linear subspace, as we showed here. If some set can be written in this way, then it's called a hyperplane. And now we said this is just the HFR, and that is the L. So that means L is a hyperplane. Okay. So that's to finish the one direction. Now let's show the other direction. suppose that L is a hyperplane. They want to show that there exists some linear functional f and a real number r such that L equals to HFR. Okay, so let's see the other direction. Okay, so to show this direction, let's think about, so suppose, in this case, suppose that we know it's a hyperplane. Then, because it's a hyperplane, we know it can be written as x naught plus some maximal linear subspace. Okay, so we know this. And now for any x in this space, we know that since M is maximal, we know that there exists some x naught. This is because M is maximal, right? It's maximal means that there exists some x in the space such that the x is just a direct sum of these two sets. And this means that for any point x in this space, we can rewrite it as there exists some a from R and x prime from, let me use y from M such that x equals to a x naught plus y. Right? So actually, even if x is not, say, let me just put it in this way. For any x in this way, we know that there exists the a and the y such that ax is written this way. So we define a functional f from x to r such that the f of x, which is just f of a x naught plus y, I'm going to define this to be a. Okay? And then we just need to show that this f is linear. And hf naught is m, and also f of x naught is number 1. It's a number 1. Okay? To show this, so first, we're going to show that the f is linear. Okay, to show that is pretty easy. I just need to show that for any x, and know that if x can be written as a x naught plus y, x prime can be written as a prime x naught plus y prime. Then let's look at the f of c1x plus c2x prime. Let's see what happens to this. And we have done something similar to before. You just need to plug this x and x prime inside, and we'll get c1a plus c2a prime times x naught plus c1y plus c2y prime. And we know that this is something in the M, and this is some number times the x naught. So by the definition of f, this should be equal to the c1a plus c2a prime. And it would be easy to show that just the c1 of a x naught plus y plus c2 of a prime x naught plus y prime. And this shows that f is linear. The second thing is that the M is just equal to HF naught, because we know that any x can be written in this way. So this m is just the points. So we set here. The m is just the set of points which we have. The y is in m, but this is the same as the 0 times x naught plus y, where y is in m. And I know that for all the points that are of this form, when I apply the f, I will get 0, right? That's why this is equal to that. This is exactly what the set of points where the f is 0. That's why I get this. Okay? So that's the second one. The third one, the f of x naught is equal to, according to our definition, the a is equal to 1, so this is equal to 1, right? Just equal to the number 1. Now we can see that this is what we're looking for, because when I look at this hf1, this h of 1, this is the L. This is essentially what the L is, right? Because this L is equal, this is just x0 plus h f naught. Okay, and this f naught is just m. And according to our definition, this is the L. Okay, so L is just this. So we found this f and found this number r, which is just number 1, such that L is equal to this. Okay, that completes the other direction. Okay, actually can have a even, let's say, we can even say that this L is a closed set. And we need that, we can get that as long as the f is continuous. So actually, I want to remark here, the L is closed if and only if this f is continuous. Okay, and why is that? L is closed. Remember that L is can be written as x naught plus some maximal linear subspace M. So if L is closed, that means M is closed, right? And M is closed means that the HF0 is closed, which means that the null set of F is closed. Okay, and from here we can see that we can claim that this is true. By the way, we said that this is this statement right here is equivalent to this is closed. Oh, sorry, this is continuous. This is one of the homework problem. But this is only for a functionals. If f is a functional, then the null space of f is closed linear subspace, if and only if f is continuous. But if f is not functional, it's an operator, then we don't really have this in general. Okay, so that's the proof. Okay, so now we get back to the original question. How should we interpret the Hahn-Banach theorem geometrically? So the Hahn-Banach theorem actually tells us a way to separate two sets or a point from separate a point from a set using a hyperplane. So rough idea is this. Say we have a convex set like this, and there's a point outside. Then there must be some hyperplane that can separate these two. Okay? Or if we have two convex sets, there should be some hyperplane that can separate these two. Okay? And we're doing, so this is pretty clear from finite dimensional. For example, this is 2D, it's two-dimensional Euclidean space. In high-dimensional Euclidean space, it's still true. But the question is if we can extend this to general linear space. Okay? In particular, we want to see if this is true for infinite dimensional Banach space. Okay, so we first define the separation of two sets. We see that two subsets E and F, so these two are subsets of X. We say these two can be separated by a hyperplane particular. We said the hyperplane is nothing but the HFR for some linear functional f and the real number r. Okay, if the f of x is less than or equal to r for any x in E, and f of x is greater than or equal to r for any x in F. If this is the case, then we say that the E and F can be separated by this hyperplane. Okay, so back to the example I showed earlier. That means, so this might be the hyperplane where the function f takes the value r. So here, this is the where f takes the value r. Okay, or this is the point such that f of x equals to r. And then on this side, it is f of x less than or equal to r. So this is the E. And this side, the f of x is greater than or equal to r. Okay, on this side. So that's the meaning of the separation. Okay, so the first thing that we're going to talk about is the separation of a point and the convex set. So let's see how do we do this. We first try to separate the point from a convex set. So let x be, see, we need a new norm now, so we need a B star space. E is a proper convex subset of X. And that will also require the 0 to be an interior point of E. Okay. If X naught is not inside E, it's outside of E, then we claim that there exists a hyperplane that can separate X naught and E. Which we denote by HFR, that separates the X naught and the set E. Okay, so that's what we were trying to prove. Okay, so again, picture-wise, pretty clear. That's the set E, and the X is something outside. It could be even on the boundary of E, but it's not inside E. Okay, and then there will be a way to separate the two. Okay, let's see how do we do this. Say, or first consider the Minkowski theorem functional. This is been a while ago. We used we defined the the Minkowski's functional of this set E, which is defined as follows. The P of X is defined to be the infimum of all the positive real numbers such that X over this A is inside E. Okay, so for each point X in the space, we define the P of X to be a non-negative number, which is the infimum of these positive numbers such that X over A is in E. And we know that the point is in E, then the P of X must be less than or equal to 1, right? And if a point is outside of the E, then P of X must be greater than or equal to 1. Okay, so that's what we know. Several properties about that Minkowski's functional. So besides this, we also define X naught. We define it to be the linear span of X naught. And we will also define this F. So F naught is a mapping defined by, so F naught can be applied to any element in the X naught. So element in X naught is given by this form. And we're going to define this to be the A times P of X naught. Okay, I know that this is a real number because P of X naught is a real number, and I'm going to show that this is a linear. Okay, so I'm going to define this F naught in this way, then it's pretty easy to show it is linear. So I guess I can skip that since we have done something similar and even more complex than this. Okay, we can show that F is actually linear. And also, we look at the F naught of X for any, so for any X equals to AX naught in the subspace X naught, we have this equal to F0 of AX naught. And because F naught is linear, we can show that this is just A times F naught X naught. Okay. And you know that this is just equal to A times P of X naught. Okay. So if A is positive, then we know that this is just equal to P of AX naught. But A could be negative. In that case, this will be negative, and this is positive. So together it's a negative number. But this is always greater than 0, greater than or equal to 0. So that's why this inequality still holds. We can change it to inequality of that. And that is equal to the definition just the px. Okay, so for any, so we found this linear subspace X naught, and we have a linear functional on it, such that, and also we have a sublinear function P, which is a Minkowski's functional, a sublinear functional. We show that there's a linear subspace, there is a F0 linear functional defined on X0, and also this F naught is bounded above by this P, by this sublinear functional. So by the Hahn-Banach theorem, we know that this F naught can be extended to a linear functional F on the whole space. Such that F, when we restrict it to X naught, is just equal to the original F naught. And also the F is bounded above by P. Right? That's what Hahn-Banach theorem tells us. Okay. So from here, you can see that df of x naught, because x naught right now is in the space, and I know that in this case, it takes the same value at that, and then we know that by definition this is equal to 1. Okay, that's one thing we know. And because f is bounded by p, so f of x, if x is from the convex set E, we know this f of x is always bounded by f of x. This is bounded by this p. But remember, for any x in E, the p of x must be less than or equal to 1. Right? This is the property of Minkowitz is functional for a convex set. The p of x must be less than or equal to 1 for any x in E. Okay? So we show that now we have a linear functional that takes the value 1 at the point x naught and takes the value less than or equal to 1 for all the points in E. So that means at least we can find this is the E, this is the point x naught. Then I know that there's a hyperplane that takes the value 1 fx. This is where the points that have factory value f equal to 1. And on this side, this is the where the f of x must be greater than or equal to 1, less than or equal to 1. Okay, so we found the separation of the two. Okay, so this is just in case that, because we didn't say if this point is on the boundary, say if the point is the E, this is the point x naught, then that's the best we can get. Okay, if the x naught is separated, we'll show another theorem later. If x naught is actually not on the boundary of E, then we actually can find something in between. But right now, since we didn't specify that, then we can only show that there exists a plane that takes the value 1 in this case at the point x0 and takes the value less than or equal to 1 for all the points in here. Okay, so that's the separation of the two, a point and a convex set. Okay, so now you can see we required the 0 to be in the null space, to be in the interior, right here. Okay, and only in this case the we require this because we needed this f to be, this E to be absorbing. So, but this is not strictly. We don't have to be, the 0 doesn't have to be in the interior. It would be any, as long as the interior of E is non-empty, then we can always do a translation, right, such that 0 is the interior point. Okay, so that doesn't really matter. But the key is that it must have an interior point. In the infinite dimensional case, that must have an interior point. So that's something you need to be careful. So when you're trying to separate two convex sets or a point from a convex set in the infinite dimensional space, make sure that the point, the convex set contains an interior point. Okay. And also we can show that this f is continuous in this case because f is bounded above by p, right? So the negative negative fx is equal to f of negative x is still bounded by p of negative x, but this is just the p of x. Oh, sorry, not necessarily, but the key is that this 2 implies that the absolute value of f of x is less than or equal to the maximum of the px and the p of negative x. For every point x, I know that this is true. Okay, and in particular, when x goes to 0, I know that the right-hand side should go to 0. Right, this is also one reason why we require 0 to be in the interior. Okay, and in this case, we know that the right-hand side will go to 0. Okay, and therefore the f is continuous at 0. So on the one hand, we know f is linear. Now we know that f is continuous at 0. We know that in this case, f is continuous everywhere, right? That's a property of linear functionals. If it is continuous at the point 0 if and only if it is continuous at everywhere. Okay, so that's the actually we can show that this f that we use to construct the separation of the hyperplane is actually continuous. Okay. Now let's consider separating two convex sets. As we hoped before, say we have two convex sets, we try to separate them. Okay, so let's say we have two convex sets. We have E1 and E2 convex sets of the space X. And the two do not intersect at this joint. Okay. And one of them has a non-empty interior. So let's say the interior of E1 is non-empty. Then the claim is there exists some S and F as a linear functional such that, so this X is the B star space, okay, a linear functional F such that the HFS separates E1 and E2. And that means the f of x is less than or equal to s for any x in E1, and also the f of x is greater or equal to s for any x in E2. Okay, that's our claim. Okay, so let's prove. Let's prove this. The idea is try to convert this problem into the previous case where we just separate the point and the convex set. Okay. Okay, let's see how do we get that. The idea is that we first take a difference of these two. Okay, we denote this E to be the E1 minus E2, which is just the points of this form, x1 minus x2, where x1 is from E1, x2 is from E2. Okay, so now you can see that, or we can easily show that this is the convex set. Again, a convex set. Why is that? Because for any 2 points, say x1 minus x2, and x1 prime minus x2 prime. So any 2 points in this set, we make a convex combination of the two. And apparently this is equal to lambda x1 plus 1 minus lambda x2 plus lambda x1 prime. And lambda x2 plus 1 minus lambda x2 prime. And this is in D2. Sorry, this should be subtract. This should be E1. That's why it's still in the set E. Right? So the E is indeed this is indeed a convex set, and also because E1 has non-empty interior, so the E will have a non-empty interior. The reason is if E1 has a interior point, then that means it has some bx1 delta that is contained in E1, right? So that's why the bx1 delta minus x2 for any x2 from the E2 set must be inside here. Okay, and this shows that x1 minus x2 is the interior point of this set E. Okay, so this E is convex and has an interior point, and also the E does not contain 0, because if 0 is included in E, then that means there exists, the 0 can be written as x1 minus x2. Okay, and that's in E means that the x1 is equal to x2. But remember that x1 is from E1, x2 is from E2. So the x1, x2 right now must be inside the intersection of the two. And that's a contradiction to the two sets being disjoint. Okay, so now we proved several things. One thing is that E is convex. Second is that the interior of E is non-empty. Third is that the 0 is not inside E. So by the previous theorem, we know that we can shift this, as we said, we can shift this so that x0 is inside the E, and the E itself has a interior point. So we show that by the previous theorem, we know there exists some f, it's a linear functional, and some s, or in this case I can only say r, such that the HFS separates, this HFR separates the 0 and the E. Okay, separate 0 and E. Okay, and what this means is that the f of x, the f of 0 must be less than equal to r. It's greater than equal to r. Yeah, it doesn't matter, right? It's greater than equal to r, and f of x must be less than equal to r for any x in E. Okay, so f0 must be 0. We know that because f is linear. So f0 must be 0. So this means that r must be non-positive, right? It must be less than or equal to 0. Because if r is greater than 0, then there's no way that f0 is 0. Okay, so this implies that the r must be less than or equal to 0. And then look at this. This is equal to f of x1 minus f of x2, because x can be written as x1 minus x2. Okay, and this means that f of x1 minus f of x2 must be less than or equal to r, and it must be less than or equal to 0. And this implies that f of x1 must be less than or equal to f of x2. Right? And this is true for any x1 in E1 and x2 in E2. Okay? So in this case, you can see that the two sets are separated. Right? These two sets are separate. So you can choose S to be between the supremum of f x1 for x1 in the E1 space, and take the infimum of f x2 for x2 to be this E2 space, and there must be some gap in between. Right? You know that these two, we must have this less than equal to that. Right? So you know that. Particularly this is because, let's just say one more word about explaining this. From what I have here, we know that for every fixed x2, the f of x1 is less than that. So that's why when we take the supremum on the left-hand side, it will be less than or equal to this. So this is the less than or equal to f of x2 for any x2. And then you take the infimum on the right-hand side. then it's still greater than, this is still less than equal to. Okay, so that's how we get this one. So this must be less than equal to this. That's why we can choose the S. And once you choose the S, you know the H f of S is the separating plane, hyperplane. Okay, so that's the proof. Okay. By the way, we don't really need this E1 to be E2 to be disjoint. We can make this slightly weaker. We can see that as long as the interior of E1, E1 is the one that has interiors. As long as this is true, then we can still find this plane. The reason is, if you have that, you can apply the same proof as before, and then we'll be able to find the HFS that separates these two. Okay, and we know that on the one side, this you must have the f of x less than or equal to s for any x in the interior of E1. But f is continuous. So if fx less than or equal to s for all the interior, this means that f of x will be less than or equal to s for any x in the closure of the interior of E1. But this closure of the interior is actually the closure of the original set, which even contains the E1. So that means that for any point in E1, f of x must be less than or equal to s. And on the other hand, f of x must be greater than or equal to s for any x in E2. Okay, so this hyperplane still separates these two sets. Okay, so that's the case. So geometrically, that means, say I have two sets which are touching each other, but one of these two sets, say for example, this one has, this is the E2, this E1, it's like this. I'm taking the interior, that will be just this. Okay, and then when we close it, it's still fine. We still can find a plane that separates the two. Okay, so that's the idea. Okay. So now let's look at the theorem, the result we mentioned earlier. Suppose that this point x, you have a point x that is a little bit far away from the convex set. So this is the convex set, let's say it's E. And you have a point x here, or x naught here. Then we actually can find something that's strictly separated the two. That means, so if this f of x equals to, say, s, this is the points where f of x equals to s, then we can show that the f of x naught is strictly less than s, and the f of x is strictly greater than s for any x in E. Okay, we want to show this. So this is the theorem we're going to prove. So again, let X be a B-star space. Okay, and also the E is a closed convex set. Okay, we want the E to be closed. Then, for any X not in, sure, I should say, for any X that is not inside E, there exists a hyperplane, which means that there exists F in X star and also some S, such that the f of, as we said, if f of x naught is going to be less than s, and this is less than, let's say the other way around. This is less than s, less than f of x naught for any x inside E. Okay, so I will change this. Okay, so let's see how to prove this. So the closed is very important. When you have the closedness, this is just in case that if it's not closed, then you have the E like this. And if the point x naught is on the boundary, then we cannot find this strict separation. right? So the E has to be closed. But when E is closed, we know that E complement is open, right? It's open. And now the X naught is from E complement. So that means X naught is the interior point of the E complement. So there exists a ball which is completely inside the E complement. Okay, and remember this ball is also convex. So now we have two convex sets, this ball and the E. So by the previous theorem, we know that there exists some F and also some S, such that the HFS separates this ball, X naught delta, and this E. Okay, so in other words, the f of x I should say the supremum of f of x for x in E will be less than or equal to the infimum of f of x for x in the ball. Okay, because that's how we can get this separation. Okay, so the S doesn't matter. I'm going to decide the S later, but this F can be used to separate the two. Okay, the question is how do we get this S? How do we get this S? This S is going to be, we can find this as follows. I'm going to show that this is not, is in fact a strict inequality. If this is true, then I can see that this will be two different numbers on real line. Okay, and then I will be able to find some S in between. Right, as long as this is two different numbers. So this is supremum of, so this is the left hand side. This is the left hand side, this is the right hand side. This is left and this is right. Okay, as long as I can show these two numbers are actually different, then I can do that. Well, how do we show that these two numbers are different? I'm going to claim that the f of x naught must be bigger than the infimum of f of x. The x is b x naught delta. Okay, so we actually proved something like this in the homework, but I can actually prove this also here using a different way. For example, I want to show this is true. If not, now that means f of x naught is equal to the infimum of f of x, where x is in b x naught delta. So that means inside this ball, with the radius delta, the f of x naught taking the infimum value. And what happens from there is that because the f is non-zero, okay, we know there exists some y in the space x such that the f of y will be, say, positive. Because non-zero, it must be take some non-zero value somewhere. And from here, we can look at x minus, I'm going to find some point in this ball such that the f takes a even smaller value than the f of x naught, and that will give us a contradiction. Okay, how do we find this point? I just subtract x naught by this y, but the y might be too large, so I'm going to normalize its y, so that has length 1. I'm also going to make it inside the ball, so that's how I make it half the radius. So I know that this will be inside the b x naught delta, right? But on the other hand, let's look at the f of this point. Okay, because f is linear, so f of x naught minus delta over 2, and even 1 over y, and this f of y. But anyway, this is positive. This is positive, right? So I subtract something, that means this must be less than f of x naught. So we found some point in this ball whose value is even smaller than the f of x naught, which is infimum, and that is impossible. That's why we have to have this strictly greater than that. Okay, strictly greater than that. So because of this, we can choose. I'm sorry, I should say that this is always smaller than that. This is always smaller than that, but the fx naught must be greater than the supremum of the f of x, where x is in the E. Okay, so I can show this is less than or equal to the infimum of f of x over this. But we just we showed this because of the existence of this separation plane or separation hyperplane. But on the other hand, we show that this is also true. So that means as 2 points on the real line, one is this, I call it L, and the other one is this, which is R. So this is the L, this is R, and I can find some S in between. Okay, and for this S, the this is the f of x. And we already found this f. So what this tells us is that the f of x must be less than s. Because we can choose this as to be, say, this s, this r. I don't know if the, let me say this one. This is the infimum of fx, where x is in the ball. This is the supremum of fx, where x is in E. I don't know if these two collapse or not, but the point is that this larger one, the infimum, must be less than or equal to R. That's why I can choose the S in between. And in this case, you know that the supremum of fx for x in E must be less than S. And this means that f of x must be less than S for any x in E. Okay, but on the other hand, I know I chose this as to be smaller than f of x naught. So that's how I get this claim. Okay, show that there is such a S, such that this is strictly less than S and this is strictly less than f of x naught. Okay, that's the proof. Okay. Another theorem we can see is about separating a convex set and a hyperplane, or a linear subspace, actually a linear manifold. Just in case that, for example, we have a convex set in 3-dimensional space. Okay, this is in 3-dimensional space. Okay, we have a convex set, and we also have a linear manifold, which could be just a line. Okay, and in this case, we say that there exists a hyperplane that contains this set. We call it the F, and this is the convex set E. There exists a hyperplane that contains this F. Let's say it's like this, such that the E is on only one side of this hyperplane. Okay, so that's the theorem I'm going to prove here. Okay. So let X be a B star space. E a convex subset. And also the interior of the E is not empty. F is a linear manifold inside X. And also the interior of E in F does not do not intersect. Okay. Then the claim is that there exists a hyperplane L that contains F, and E is on only one side of the hyperplane. Okay, that's what we as showed in the picture. Okay, so how do we prove this? First of all, the F is a linear manifold, so that means F can be written as x naught plus some x naught, where this x naught here is in x, and this x naught is a linear subspace of x. Okay, it may not be maximal. As we said, if it's a line, then it is x naught is not maximal. Okay, and also because this F is a convex set, right? It's just shifting of a plane, shifting a linear subspace, so it's a convex. And also the E is convex, or interior of E is convex. Okay, and that means there exists, by the previous theorem, there exists some F that's a linear, and also this is linear, and also there exists some R, such that the f of x is less than or equal to R for any x in E, and also f of x is greater than or equal to R for any x in F. Okay, so I'm going to denote this S to be the f of x naught. Where this x naught is this one, right here. Okay, I define this S to be that value. Then, so that this, then for any x prime in x naught, we know that f can be written as x0 or x naught plus some point in here. So every element in f can be written as x naught plus x prime, where x prime is from here. Okay, so from here we know that the f of x, where this x is in f, can be written as f of x naught plus x prime. Right, this one is in x naught. Okay, so on the one hand, this is equal to that plus f of x prime, and this is equal to s plus f of x prime. On the other hand, f of x, we know that it has to be greater than or equal to r. Okay, so greater than or equal to r. So this means that f of x prime, so f of x prime, is greater than or equal to r minus s for all the x prime in x naught. Okay, and again, because x naught is a linear subspace, so it contains 0. Right, 0 is in here. So if we put 0 here, then we'll have f of 0 greater than or equal to r minus s. But remember that f0 must be 0. So this means that r minus s must be less than or equal to 0, or r must be less than or equal to s. Okay, that's what we know. And also, because x naught is a linear subspace, and we're going to claim that this f actually takes the value 0 in the entire linear subspace. I'm going to claim this. Why is that? On the one hand, we know that, so let's prove this by contradiction. Suppose it's not true, then that means there exists some x prime such that f of x prime is non-zero. Let's say it's positive. And then, because this is positive, so if I multiply a negative number, very negative number, to this, say it's negative a times x prime, where a is a very large positive number, then this will be less than 0. Not just less than 0, but it will be also less than r minus s. Okay, because we can make this arbitrarily small, or arbitrarily negative. Okay, and notice that this is still in x0 because x0 is a linear subspace. So when x prime is in x0, then any scaling of x prime is also in x0. So this is in there, and this is a contradiction to that. This must be greater than or equal to r minus s for all the x prime, for all the points in x0. Okay, so that finishes the proof of the claim. Okay, so we claim that the f of x prime is equal to 0 in the entire x0. So from here, we know that x0 will be inside hf0 because x0 should be a subset of the null space of f. Okay, and from here we know that f as x0 plus hf0 should be equal to hf. Remember, this just should be the value of f of x0, which is s. Okay, so we know this. On the other hand, so this means that f of x equals to s for any x in f. Okay. On the other hand, we know that for any x in E, we have f of x less than or equal to r. Right, this is what we said before. F of x must be less than or equal to r. But here, this tells us that r is also less than or equal to s. So this is less than or equal to s for any x in E. Okay, so what we showed is that we found this linear function on f that is equal to s for all the points x in f, and is less than or equal to s for all the points that is in E. So this corresponds to this one. So we found this hyperplane such that on this hyperplane, all the function values takes the value s, and on one side of this, it takes the value less than or equal to s, and the E is contained in one side of this hyperplane. Okay, that completes the proof.